Rogue planets are fascinating objects in space. They don't follow the usual pattern of planets orbiting a star. Instead, they drift through space on their own, far from any star's warmth or light. You might imagine them as lonely travelers, moving through the vast emptiness of space without a fixed destination. These planets are often mysterious because they are hard to spot. They do not glow like stars, nor do they reflect much light like moons or asteroids. This makes them tricky to find and study. Rogue planets are not a recent discovery. Scientists have known about them for years, but the idea became clearer in the 1990s. It was during this time that astronomers began to realize how common these wandering planets might actually be. Rogue planets can vary in size. Some are small, like Earth, while others may be as large as Jupiter or even bigger. Their size, however, is not what makes them stand out. It's their ability to travel alone through space, outside the pull of any star. To understand how a rogue planet comes to exist, it helps to think about the journey of a planet. Most planets form in a solar system. Over millions of years, dust and gas collide and stick together, growing into larger objects. Eventually, these objects become planets that orbit the star. But not every planet stays in its orbit forever. Sometimes, a planet may get kicked out of its solar system. This could happen for a variety of reasons. Perhaps the planet encounters the gravity of another large object, like another planet, or even a star. The force of this encounter could be strong enough to knock the planet off course and send it into deep space. Other rogue planets may form in regions far from any star. These planets might form in dark parts of space, in clouds of gas and dust, where stars have not yet been born. These planets are different from the ones that get ejected from solar systems. Instead of being kicked out, they simply never had a star to begin with. They grow and develop in isolation, slowly drifting through space. The idea of a rogue planet is not just interesting because it's different from other planets. It also raises questions about how many such planets might exist. Some scientists believe that rogue planets could be quite common. In fact, they may outnumber the stars in the Milky Way galaxy. If this is true, there could be billions of rogue planets in our galaxy alone. The idea is hard to imagine considering how dark and distant these planets are. But the math and models suggest that they could be everywhere. One reason rogue planets are hard to detect is that they do not emit their own light. Unlike stars, which shine brightly, rogue planets are dark and cold to see them. Astronomers rely on indirect methods. They look for signs that a rogue planet might be passing in front of a distant star. When this happens, the light from the star may briefly dim. This dimming effect, called gravitational microlensing, can help scientists spot objects that are otherwise invisible. It is through this method that astronomers have been able to find a few rogue planets. Another way to find rogue planets is by using infrared telescopes. These telescopes can detect the faint heat emitted by the planet. Since rogue planets are not close to a star, they are cold and not as bright as other objects in space. However, if a planet is large enough or young enough, it might still be hot enough to be detected in the infrared spectrum. Despite the challenges in detecting rogue planets, scientists have made some interesting discoveries. For instance, in 2016, astronomers found a rogue planet about 100 light years from Earth. This planet, called CFB-DESA 2149, -0403, was found using data from the Canada-France-Hawaii telescope. It was one of the first rogue planets to be confirmed. It's not the only one, though. Many more have likely been discovered or will be in the future. Rogue planets also offer interesting possibilities when it comes to life. If a planet drifts through space far from a star, it would be extremely cold. Without the warmth and light of a star, it would be hard for life as we know it to survive. However, some scientists suggest that life could still exist on rogue planets. They believe that these planets might have internal heat generated by radioactive decay or tidal forces. This internal heat could provide the warmth needed to support life in the form of extremophiles, organisms that can live in harsh conditions. It's also possible that these rogue planets might pass close enough to a star during their journeys to temporarily warm up and create conditions suitable for life. In addition to the possible presence of life, rogue planets could be important for understanding the history of solar systems. A planet that is ejected from its original solar system could tell us a lot about the dynamics of that system. It could reveal information about the interactions between planets, the behavior of gravity, and the way planets form. Studying these planets might also give us clues about how our own solar system works and how it might evolve in the future. In the search for rogue planets, astronomers are just scratching the surface. The more they study, the more questions they find. The existence of rogue planets challenges our understanding of how planets behave. It also forces us to rethink the idea of what it means for a planet to have a home. Without a star, a rogue planet is truly on its own, drifting silently through the cosmos. This isolation makes them unique objects in space, offering a glimpse into the mysteries of the universe. While they may never be as easy to find as planets that orbit stars, rogue planets are still a part of our universe. They are a reminder of the vastness and unpredictability of space. Whether they were ejected from their home solar system or formed in isolation, rogue planets challenge our understanding of what planets are and how they can exist. They are not bound to a star, but they are bound to the same forces that shape all objects in space. And though they are distant and cold, they remain one of the most intriguing discoveries in modern astronomy. For many years, scientists searching for signs of extraterrestrial life have focused on planets that orbit stars. These planets, located in what's called the habitable zone, are thought to have conditions that could support life. The habitable zone is the region around a star where temperatures allow liquid water to exist. Water is considered essential for life, as planets in this zone are prime candidates for the search for alien life. But there's another type of planet that has been largely overlooked in this search: rogue planets. Rogue planets don't follow the usual pattern. Unlike most planets, they don't orbit a star. Instead, they wander through space, drifting alone in the vast emptiness. Rogue planets are often too cold and dark to be noticed easily. But recent discoveries suggest that these wandering worlds might offer a new opportunity in the search for extraterrestrial life. To understand how rogue planets could support life, it helps to think about what makes them different from regular planets. Most planets are found in solar systems, locked in orbits around their stars, but rogue planets have been ejected from their home solar systems. Or they may have formed in isolation in dark regions of space, far from any star. Because they are not near a star, they are often freezing cold. Without the warmth of a star, these planets would not seem like suitable places for life. But the situation might not be as bleak as it first appears. Rogue planets may still have internal heat generated by radioactive decay or the tidal forces of their moons. If they have any, this internal heat could keep the planet warm enough for life to exist, even without the light of a star. In fact, there are organisms on Earth called extremophiles that live in extreme environments such as deep ocean vents where there is no sunlight. These organisms survive by using heat from the Earth's core and chemicals in the water. While rogue planets are cold, they are not entirely devoid of heat. Some may have retained warmth from when they were formed, and they may continue to emit heat from their cores. In some cases, the planet might even pass near a star during its journey through space. This brief encounter could warm the planet enough to create a temporary environment where life could exist. This kind of scenario, though rare, opens up possibilities that we have not fully considered in the search for alien life. The idea of life on a rogue planet challenges our traditional understanding of where life can exist. For decades, scientists have focused almost exclusively on planets in the habitable zone of stars. But rogue planets present an interesting alternative. The conditions on these planets may not be what we're used to, but that doesn't mean they couldn't support life. In fact, the discovery of even a single rogue planet with signs of life would change how we think about the universe. One of the key challenges in finding life on rogue planets is that these planets are hard to detect. Without a star, rogue planets don't shine like stars or reflect light like moons. They are dark and cold, making them nearly invisible to traditional telescopes. However, astronomers have developed new techniques for spotting these hidden planets. One of the most important methods is gravitational microlensing. This technique works by observing how the gravity of a rogue planet can bend and distort the light of a distant star. When a rogue planet passes in front of a star, it can cause a brief dimming of the star's light. This change in brightness can alert astronomers to the presence of a rogue planet. In addition to gravitational microlensing, infrared telescopes can also help in the search for rogue planets. These telescopes can detect the faint heat that a rogue planet might emit. Even though these planets are cold, they are still warm enough to be detected in the infrared spectrum, especially if they are relatively large or young. By using these advanced techniques, astronomers are beginning to uncover more about rogue planets. And with that knowledge comes the possibility of discovering alien life. If rogue planets can support life, it would dramatically change how we think about the potential for extraterrestrial life in our galaxy. In the past, we've assumed that life requires a planet to be in the habitable zone of a star. But rogue planets suggest that life might be possible in far more places than we ever imagined. These wandering planets could be home to forms of life that we have yet to even consider. The key challenge, of course, is figuring out how to detect signs of life on a planet that is so far away and so dark. The search for life on rogue planets is still in its early stages, but the possibilities are intriguing. Imagine a scenario where a rogue planet drifts close to a star. The heat from the star could provide a brief window of warmth, and life could take hold during that time. Or the planet might have enough internal heat to keep things warm for longer periods. In either case, life could develop and survive in conditions that we once thought were impossible. One important consideration is the type of life that might exist on a rogue planet. It is likely that life here would be very different from the life we know on Earth. On Earth, life depends on sunlight, oxygen, and water. On a rogue planet, life would need to adapt to the lack of sunlight. It might rely on chemical reactions or internal heat sources rather than photosynthesis. This type of life would be radically different but not impossible. As we continue to explore space and improve our technology, the search for extraterrestrial life will likely expand to include rogue planets. These wandering worlds may seem isolated and inhospitable, but they could offer new opportunities for discovery. If rogue planets can support life, then the number of potential places for life in the universe increases dramatically. This could have profound implications for our understanding of life, the universe, and our place within it. The discovery of life on a rogue planet would not only answer important questions about where life can exist, but also open up entirely new areas of exploration in the search for extraterrestrial life. Exoplanet exploration has long focused on planets orbiting stars, especially those in the habitable zone, where conditions might support life. These planets are considered ideal candidates because their proximity to a star allows liquid water to exist on their surfaces. However, in recent years, astronomers have begun identifying rogue planets, planets that don't orbit a star. These planets roam freely through space, far from the influence of any star. While the idea of life on such planets might seem far-fetched, some scientists believe that rogue planets could harbor the right conditions for life, even without the warmth of a host star. rogue planets have been ejected from their original solar systems, or they may have formed in regions far from any star. Unlike the planets we are most familiar with, these rogue worlds do not bask in the light or heat of a nearby star. Instead, they drift through the cold vacuum of space, often in complete isolation. Their dark, frozen nature makes them difficult to detect with traditional methods. However, astronomers have developed ways to spot these wandering planets, using techniques like gravitational microlensing, which helps reveal objects that are otherwise invisible. Despite their cold temperatures, rogue planets are not necessarily lifeless. The search for signs of life on these planets is still in its early stages, but the possibilities are intriguing. While it may seem that a planet without a star would be inhospitable, rogue planets might still have internal heat. This heat could come from the planet's core, generated by radioactive decay, or the gravitational forces from moons or other nearby objects. Just as Earth's core provides heat that fuels volcanic activity and supports life deep beneath the ocean, rogue planets might have similar sources of warmth. These heat sources could be enough to create pockets of warmth on the planet's surface, which might be suitable for life. The idea of life on a rogue planet might sound strange at first, but it's not completely out of the question. Life on Earth exists in many extreme environments, from the freezing polar regions to the boiling deep ocean vents. These environments lack sunlight, yet they still support diverse ecosystems. Extremophiles, organisms that thrive in extreme conditions, have adapted to survive without the sun's energy. On rogue planets, life could potentially survive in a similar way, relying on chemical energy from the planet's core or from chemical reactions occurring deep underground. These organisms might not look or act like the plants and animals we know, but they could be just as complex and diverse in their own way. One of the key questions in the search for life on rogue planets is whether they have enough heat to support life. While the surface temperature of a rogue planet may be extremely cold, the internal heat from the planet's core could play a critical role. Some scientists believe that rogue planets could have a relatively warm core, enough to maintain a liquid water environment beneath the surface. If this is true, it could provide the necessary conditions for life to survive. Life on Earth, for example, depends on liquid water, and any potential life on rogue planets would likely need water in some form as well. Astronomers are still in the process of discovering rogue planets, but the potential for life on these planets opens up new possibilities for exploration. For instance, consider a rogue planet that has recently been ejected from its solar system. This planet might have once been close to a star, providing it with the necessary warmth to support life. As it drifts further from its original star, it may still retain some of that heat, which could provide a brief window in which life might thrive. The planet might not have the same conditions as Earth, but life could survive on a rogue planet in a similar way that life survives deep in the ocean or in underground caves. Finding a rogue planet with conditions suitable for life would be a major breakthrough. These planets may seem isolated and cold, but they could harbor the right conditions for life to take root. As technology improves, astronomers may be able to detect more of these planets and study them in greater detail. While many rogue planets may not be suitable for life, there could be some that have the right conditions. These planets might have enough internal heat, and perhaps even underground oceans that could support life forms. However, the search is difficult. Rogue planets are small, dark, and distant, and they do not emit light like stars or reflect it like moons. The search for these planets requires new methods of detection and advanced technology. Unpromising method for discovering rogue planets is the use of infrared telescopes. These telescopes are designed to detect the faint heat emitted by objects in space. Even though rogue planets are not close to a star, they can still emit infrared radiation due to their internal heat. In some cases, if a rogue planet is relatively young or large enough, it might emit enough heat to be detected by these telescopes. As technology advances, astronomers may be able to identify more rogue planets and examine them for signs of life. This process will take time, but it could open up entirely new areas of research. Rogue planets offer a different perspective on the search for extraterrestrial life. While most research has focused on planets that orbit stars, rogue planets represent a new frontier. These planets may not have the same conditions we associate with life, but they could still be capable of supporting life in unique ways. If life does exist on rogue planets, it would likely be very different from life on Earth, and it could be thriving in environments that we have not yet considered. The study of rogue planets may help expand our understanding of what conditions are necessary for life and how life can survive in even the most extreme environments. The search for life on rogue planets is a growing field of interest. As more rogue planets are discovered, scientists will be able to learn more about these strange and distant worlds. Some may turn out to be lifeless, but others could hold surprises. The discovery of even a single rogue planet with signs of life would have profound implications for the search for extraterrestrial life. It would suggest that life might not be limited to planets with a star, but could exist in many more places than we ever imagined. This would not only change our understanding of where life can exist, but also offer new paths for exploration in the future. Rogue planets are unique in that they do not orbit any star. They drift through space alone, far from the warmth and light of a sun. At first glance, these planets might seem like unlikely candidates for supporting life. After all, life on Earth depends heavily on the energy we receive from the sun. However, rogue planets could still offer conditions where life could survive, even without sunlight. One of the most promising possibilities is the idea that rogue planets might have subsurface oceans heated by internal geothermal energy. These rogue planets may be cold on the surface, but that doesn't mean they are completely devoid of heat. Most planets have internal heat, generated during their formation. This heat can be maintained over time through processes like radioactive decay in the planet's core. On Earth, this internal heat is responsible for geological activity, like volcanoes and earthquakes. In the case of rogue planets, this heat could create a layer of liquid water beneath the surface, kept warm by the planet's geothermal activity. Subsurface oceans on rogue planets could be similar to those found on Earth in places like deep ocean vents. These vents release heat and minerals from below the Earth's crust, creating an environment where unique life forms can thrive without sunlight. In the deep ocean, organisms called extremophiles survive in complete darkness, relying on the heat and chemicals from the vents instead of the sun. If a rogue planet has a similar geothermal system, it could support life that depends on these underground ecosystems rather than sunlight. The heat from a rogue planet's interior would not need to be extreme to create a habitable environment. Even a small amount of heat, trapped beneath a thick layer of ice, could keep water liquid in certain regions of the planet. This would create a stable, warm environment beneath the surface. The water in these oceans could be rich in minerals, providing the right conditions for life to form and survive. The organisms living in these oceans might use the planet's geothermal energy in much the same way that life forms on Earth use sunlight or chemical energy. One possible scenario could involve a rogue planet with an icy crust. The surface temperature might be so cold that water would freeze, making the surface uninhabitable. However, beneath the ice, the geothermal heat from the planet's core could keep an ocean of liquid water. The warmth of the ocean could also provide enough heat to support life. Similar to how deep ocean life forms use chemicals and heat from vents, life on a rogue planet could use geothermal energy, not sunlight, to survive. In fact, some scientists believe that the oceans of rogue planets could be very similar to the oceans on Earth. But without the sunlight, water heated by internal energy could create an environment where microbial life could thrive. The deep oceans on Earth, far below the reach of sunlight, are home to complex ecosystems of creatures that live in total darkness. These creatures survive by using the chemical energy from the Earth's core, not sunlight. If life can thrive in such conditions here, it is not hard to imagine that similar life forms could exist on rogue planets in comparable environments. In addition to geothermal heat, rogue planets could also have other sources of energy. For instance, the planet might have a moon that exerts tidal forces, causing the planet's interior to heat up. This process, called tidal heating, occurs when a planet's shape is stretched and compressed by the gravitational pull of a nearby object. This stretching can create friction inside the planet, generating additional heat. This tidal heating could be significant enough to keep water beneath the planet's icy surface in a liquid state, providing another way for life to survive. The subsurface oceans on rogue planets could also contain a variety of chemical compounds necessary for life. On Earth, life relies on a combination of elements like carbon, nitrogen, and oxygen. These elements are commonly found in water, and they are vital for the processes that sustain life. A rogue planet's subsurface ocean might also contain these compounds, especially if the planet has volcanic activity or other geological features that bring these elements to the surface. These compounds would provide the raw materials needed for life to develop and thrive, even without sunlight. The possibility of life on rogue planets is not just a theoretical idea. It is based on real examples here on Earth. Deep-sea hydrothermal vents are home to thriving ecosystems that depend on geothermal energy rather than sunlight. These ecosystems are incredibly diverse, with species that can survive in extreme conditions, such as high pressure, high temperatures, and complete darkness. Some of these creatures live on sulfur and methane, chemicals that are released from the Earth's core. The fact that life can survive in these extreme environments gives hope that similar life forms could exist in similar conditions on rogue planets. It is also worth noting that life on rogue planets might not look like the life we know. Instead of relying on sunlight, life on these planets could be based on different forms of energy. Life could thrive in the dark, heated by the planet's core, and use the minerals in the subsurface oceans for food. These life forms could be simple microorganisms, or they could be more complex organisms, depending on the conditions of the planet. The key point is that life could survive in these conditions, as long as there is a source of energy and the right chemical ingredients. Despite the challenges of life on a rogue planet, the concept is not entirely out of reach. These planets could have all the basic ingredients needed for life to exist. A subsurface ocean heated by internal energy could provide a stable, life-supporting environment. Even in the absence of sunlight, the geothermal heat could keep the water liquid and provide the necessary warmth for life to survive. The chemical elements needed for life could be present, and the planet could have a source of energy to support ecosystems, much like the deep ocean vents on Earth. The study of rogue planets and the possibility of life on these planets is still in its early stages. Astronomers are working to develop new techniques to detect these planets and study their potential for habitability. As our technology improves, we may be able to detect signs of geothermal activity or subsurface oceans on rogue planets. This could help us better understand the potential for life on these distant starless worlds. Rogue planets may not seem like the most likely places to find life, but they represent an intriguing possibility. Even without a star, these planets could have the conditions necessary to support life beneath their frozen surfaces. The idea of subsurface oceans heated by geothermal energy opens up a whole new area of exploration in the search for life beyond Earth. Rogue planets are unlike most planets we know. They don't orbit a star and drift through space on their own. While this might seem like an unlikely place for life, There's a key feature of rogue planets that might allow life to survive: the heat from their core. This heat comes from two main sources: tidal forces and radioactive decay, and it could create the warmth necessary for life to thrive beneath the planet's surface. On Earth, we rely heavily on the sunday for warmth and energy. Without the sunday, life would not exist as we know it. However, not all planets need sunlight to be habitable. Rogue planets may not have a star, but they can still have heat from deep within their interiors. This heat is essential for creating environments where life could survive, especially if the heat is used to keep water in a liquid state beneath the surface, even though the surface itself might be cold and frozen. Tidal forces are one of the key ways that heat is generated within a planet. Tidal forces occur when the gravitational pull from a nearby object, such as a moon or another planet, stretches and compresses the planet's shape. This movement creates friction inside the planet, which generates heat. This process, called tidal heating, is most noticeable in planets or moons that have large orbits or significant gravitational interactions with other objects. For instance, Jupiter's moon Europa experiences tidal heating because of its orbit around Jupiter. The constant pull and release of gravitational forces generate enough heat to keep subsurface oceans liquid, even though the surface is covered in ice-rogue planets, while not orbiting a star, can still experience tidal forces. If they have moons, or are in close proximity to another massive object, like a gas giant, the gravitational interaction could stretch and compress the planet's interior. Over time, this friction generates heat, which can maintain a warm environment beneath the surface. Even in the cold vastness of space, this heat could create conditions where liquid water exists underground, providing a potential habitat for life. In addition to tidal heating, another source of heat for rogue planets is radioactive decay. Planets, including rogue planets, contain radioactive materials in their cores. These materials slowly decay over long periods, releasing heat in the process. On Earth, this geothermal heat drives volcanic activity and supports life deep below the ocean. The same process could occur on a rogue planet, providing enough warmth to sustain subsurface oceans. The key difference between tidal heating and radioactive decay is how they work. Tidal heating relies on external forces such as the gravity of nearby moons or planets to create heat through friction. Radioactive decay, on the other hand, is an internal process, occurring within the planet itself. Both processes could work together to create a stable source of warmth that could support life below the surface. In a rogue planet, this combination of tidal heating and radioactive decay could allow the interior of the planet to remain warm, despite the cold, dark environment outside. Beneath the frozen crust, a liquid ocean could exist, much like the deep oceans on Earth. These oceans could be rich in minerals and nutrients, providing the right conditions for life to emerge. In fact, scientists believe that life could exist in these environments, in ways similar to the extremophiles that live around Earth's deep-sea hydrothermal vents. These organisms thrive without sunlight, relying on chemical energy and heat from the planet's interior instead. This process is not just theoretical. Earth's deep ocean ecosystem is an example of how life can thrive in the absence of sunlight. Deep-sea creatures live near hydrothermal vents, where water heated by the Earth's core provides a stable environment for life. These organisms rely on chemicals like hydrogen sulfide, which is released by the vents rather than sunlight for energy. The same principle could apply to rogue planets, where life could survive in underground oceans, relying on heat and chemicals from the planet's core. In a scenario where a rogue planet has an icy crust, the heat from the planet's core could melt the ice, creating a liquid water environment beneath the surface. This warmth could support a variety of life forms, from simple microbes to more complex organisms. The planet's interior heat would act like a furnace, providing the necessary energy to keep the water from freezing solid, even in the cold vacuum of space. While life on rogue planets might be different from life on Earth, it is still possible. The organisms living beneath the surface would likely not rely on sunlight for energy, but instead on the heat and chemicals coming from the planet's core. The geothermal energy on these planets could create a stable and self-sustaining environment, similar to the ecosystems found in Earth's deep oceans. These organisms could live in total darkness, just like the extremophiles at the bottom of Earth's oceans, relying on heat and chemical energy rather than light. The idea that rogue planets could have the necessary warmth for life challenges our traditional understanding of habitability. We usually think of planets with stars as the most likely places to find life. These planets are in the habitable zone, where temperatures are just right for liquid water to exist on the surface. However, rogue planets suggest that life could also survive in the absence of a star, as long as there is enough heat within the planet itself. The discovery of life on a rogue planet would force scientists to rethink what makes a planet habitable and expand the search for life beyond the traditional boundaries. The detection of rogue planets and their potential to support life is a growing area of research. As technology advances, astronomers will be able to study these planets in more detail. They may be able to detect signs of tidal heating or measure the heat coming from a planet's core. This would help determine whether a rogue planet has the right conditions for life. Over time, the study of these planets could reveal new insights into how life might form and survive in the most unlikely of places. Life on rogue planets might seem far-fetched, but the combination of geothermal energy from tidal heating and radioactive decay offers a viable way for life to exist. Just like life on Earth thrives in deep-sea vents, without sunlight, life on rogue planets could rely on the heat from the planet's core. These planets could host subsurface oceans that provide the warmth and energy necessary to sustain life, despite the cold emptiness of space around them. This possibility opens up a new frontier in the search for extraterrestrial life and challenges our understanding of where life can exist in the universe. Rogue planets, which drift through space without a star, are often seen as cold and inhospitable. Without the warmth of a nearby sun, these planets might seem like places where life could never exist. However, some rogue planets might not be as lifeless as they first appear. One feature that could make these planets more livable is the presence of a thick atmosphere. If a rogue planet has a thick atmosphere, it could trap heat through a process similar to the greenhouse effect, much like the one on Venus. This heat could create conditions on the planet's surface that support life, even in the absence of a star. To understand how a thick atmosphere can create warmth, it helps to know how the greenhouse effect works. On Earth, sunlight reaches the surface and warms it. The Earth then radiates some of that heat back into space as infrared radiation. However, certain gases in the atmosphere, like carbon dioxide and water vapor, trap some of this heat, preventing it from escaping into space. This trapped heat warms the planet, making it more suitable for life. The more gases like carbon dioxide in the atmosphere, the stronger the greenhouse effect. Venus, for example, has a very thick atmosphere made mostly of carbon dioxide, and it traps so much heat that the surface temperature is hot enough to melt lead. The greenhouse effect on Venus is an extreme example, but it illustrates how a planet's atmosphere can keep things warm. Even though Venus is much closer to the Sunday than Earth, it is its thick atmosphere, not its distance from the Sunday, that makes the planet so hot. A similar process could happen on a rogue planet if it has a thick atmosphere that can trap heat. The difference is that a rogue planet would not receive energy from the Sunday. Instead, it would need to generate and retain its own heat, which could be trapped by the atmosphere. Rogue planets, especially those that have been ejected from their original solar systems, might still have thick atmospheres from their time near a star. Planets in a star's habitable zone often develop atmospheres to regulate temperature and protect the planet from space radiation. Even after being cast out of a solar system, a rogue planet could retain its atmosphere for some time, especially if it is massive enough to hold on to it. Once the planet is free of the star's gravitational pull, it no longer gets warmth from the sunday. But if the atmosphere is thick enough, it could still trap the heat that the planet's interior produces. This would create a greenhouse effect that might keep the surface temperature warm enough for liquid water to exist. A rogue planet could also generate heat internally through processes like tidal heating or radioactive decay, which could help maintain warmth. Tidal heating occurs when a planet experiences gravitational forces from a nearby object like a moon or another planet that cause it to stretch and contract. This friction generates heat, which could help maintain a warm environment beneath the surface. Even if a rogue planet is far from a star, it could still have enough internal heat to support a thick atmosphere and create a stable environment on its surface. If this heat is trapped by the atmosphere, it could result in a climate that is relatively stable and capable of supporting life. In addition to retaining heat from internal processes, a thick atmosphere could also help protect the planet's surface from the harsh conditions of deep space. Space is a hostile environment with high levels of radiation and extreme temperatures. On Earth, our atmosphere shields us from harmful radiation and keeps temperatures within a range that is comfortable for life. A rogue planet with a thick atmosphere could offer similar protection, allowing life to survive even in a starless, freezing environment. The atmosphere could block harmful radiation from deep space and create a stable environment where water could exist in liquid form, making it possible for life to thrive. Some scientists suggest that a rogue planet with a thick atmosphere could create a kind of habitable zone of its own. This zone wouldn't be based on proximity to a star, but on the planet's ability to retain heat through its atmosphere. The greenhouse effect could keep the planet warm enough to support liquid water, even if the planet is far from any star. This idea opens up new possibilities for finding life in the universe. Instead of limiting the search for life to planets that orbit stars, scientists could look for rogue planets with thick atmospheres that could potentially support life. The key factor in determining whether a rogue planet could support life is the composition of its atmosphere. Not all atmospheres are capable of trapping heat. For example, the atmosphere of Mars is very thin and doesn't trap heat effectively, which is why it's so cold there. A thick atmosphere, however, made up of gases like carbon dioxide, methane and water vapor, could trap heat and create a warm environment. Some rogue planets might have atmospheres made of these gases, especially if they formed in the same way as planets in a solar system. If the conditions are right, these gases could trap enough heat to create a greenhouse effect that keeps the planet warm. Imagine a rogue planet that once orbited a star and had an atmosphere full of greenhouse gases. After being ejected from its solar system, the planet drifts through space. Over time, its atmosphere could cool, but it might still be thick enough to trap heat from the planet's interior. This heat, combined with the greenhouse effect, could keep the surface temperature warm enough for liquid water to exist. Even though the planet is no longer near a star, it could still have a stable climate that supports life. This scenario, though theoretical, is not impossible. In fact, some researchers believe that rogue planets with thick atmospheres might be more common than we realize. These planets could be hiding in plain sight, drifting through the galaxy with the potential to harbor life. The idea challenges our traditional understanding of habitability, which has focused primarily on planets in the habitable zone of stars. Rogue planets, with their thick atmospheres, offer a new way to think about where life could exist. Instead of relying on the light and warmth of a star, these planets could create their own livable environments by trapping heat within their atmospheres. As scientists continue to study rogue planets, they will likely discover more about the conditions that might allow life to survive on these worlds. The presence of a thick atmosphere could be one of the key factors in determining whether a rogue planet is habitable. By focusing on this feature, researchers may be able to identify rogue planets that have the potential to support life, even without the warmth of a star. The search for life in the universe may soon expand beyond star systems, including the many rogue planets that wander through space, each with its own unique conditions for habitability. Rogue planets, which drift alone through space without a star, are often seen as cold and lifeless. However, one feature of these planets might provide a surprising possibility for life: subsurface oceans. These oceans, buried beneath thick layers of ice or rock, could remain liquid because of the internal heat generated by the planet itself. This heat could come from various sources, such as tidal forces or radioactive decay. With enough warmth, these subsurface oceans could create stable environments where life could thrive, even in the complete absence of sunlight. The idea of subsurface oceans is not just theoretical. On some moons in our own solar system, like Europa, one of Jupiter's moons, scientists believe that vast oceans lie beneath thick ice shells. These oceans remain liquid due to tidal heating, a process where gravitational forces from a nearby planet stretch and compress the moon, generating enough heat to keep the water beneath the surface from freezing. This is a similar process that could occur on rogue planets, where internal heat from the planet's core or tidal forces could keep subsurface oceans in a liquid state. On Earth, life thrives in a variety of extreme environments, including the deep ocean where sunlight doesn't reach. These deep-sea ecosystems depend on heat from the Earth's core and chemicals from the ocean floor. Organisms in these environments, called extremophiles, rely on geothermal energy rather than sunlight to survive. This kind of life could exist in subsurface oceans on rogue planets, where warmth from the planet's core or other internal processes could provide the energy needed for life to develop. For a rogue planet, the heat that keeps its subsurface ocean liquid could come from two primary sources: tidal heating or radioactive decay. Tidal heating occurs when a planet experiences gravitational interactions with nearby objects, such as moons or even other planets. These interactions stretch and compress the planet's interior, generating friction and heat. If the rogue planet has moons or is in close proximity to a large object, tidal forces could produce enough heat to create and maintain liquid oceans beneath its surface. Even if the planet is far from any star, the heat generated by tidal forces could provide a stable environment for life. Radioactive decay is another source of heat within planets. Most planets, including rogue planets, contain radioactive elements deep in their cores. Over time, these elements break down, releasing energy in the form of heat. This heat could maintain a subsurface ocean in a liquid state, even if the planet is far from any star. Radioactive decay occurs over millions and billions of years, which means it could provide a long-term, steady source of warmth, allowing a subsurface ocean to remain stable for extended periods of time. These subsurface oceans would be hidden beneath thick layers of ice, rock, or both. The surface of a rogue planet could be frozen solid, with temperatures so cold that no liquid water could exist on the surface. However, beneath the ice, the geothermal heat could keep the ocean from freezing, providing a warm enough environment for life. The heat could prevent the water from freezing solid, allowing it to remain liquid and potentially creating conditions that are conducive to life. Life in a subsurface ocean would likely be very different from life on the planet's surface. Without sunlight, organisms would need to rely on other sources of energy. In the deep ocean of Earth, organisms use chemicals from hydrothermal vents to survive. These vents release heat and minerals from the Earth's core, creating an environment where life can thrive without sunlight. A similar process could happen in a subsurface ocean on a rogue planet. The ocean would likely be rich in minerals and chemicals released by the planet's core, and life could use these chemicals for energy. This kind of life could range from simple microbes to more complex organisms, depending on the conditions in the subsurface ocean. On Earth, microbial life has been found in extreme environments, such as deep-sea vents, underground caves, and frozen ice sheets. These organisms survive in conditions that seem inhospitable to most life forms, yet they manage to thrive by using the available resources. On a rogue planet, life might develop in a similar way, relying on the geothermal heat and chemicals in the subsurface ocean to survive and evolve. The key to life in these subsurface oceans would be the stability of the environment. A rogue planet, despite being far from a star, could have a relatively stable and long-term environment beneath its surface. The internal heat from the planet's core, whether generated by tidal forces or radioactive decay, would keep the ocean from freezing. The thick layers of ice or rock above the ocean could protect it from the harsh conditions of space, such as radiation and extreme cold. This insulation could create a safe and stable environment for life to exist. Zone possible scenario involves a rogue planet with an icy crust. The surface temperature of the planet could be extremely cold, with no liquid water. However, beneath the ice, geothermal heat could keep the subsurface ocean liquid. This heat could create a stable, habitable environment, with warm temperatures and a steady supply of chemicals from the planet's core. Life could survive in the darkness, relying on geothermal energy and the chemicals released from the planet's core, just as life thrives in the deep ocean on Earth. Another possibility is that the rogue planet could have a rocky surface with volcanic activity. Volcanic eruptions would release heat and chemicals into the subsurface ocean, providing an additional source of energy for life. In this case, life could thrive around underwater volcanic vents, much like the ecosystems found around Earth's hydrothermal vents. These vents could create a diverse and complex environment for life to develop, with different species relying on various chemical processes to survive. While the idea of life on a rogue planet might seem far-fetched, the presence of subsurface oceans, powered by internal heating, opens up new possibilities. These oceans could provide a stable, long-term environment for life to survive, even without the energy from a star. The process of tidal heating or radioactive decay could keep the subsurface oceans warm, while the thick layers of ice or rock above the ocean could protect it from the harsh conditions of space. This combination of factors could create an environment that is capable of supporting life, even in the cold, dark regions of the universe, where sunlight is absent. Scientists are still learning about the conditions that could make rogue planets habitable, and the study of subsurface oceans is an important part of this exploration. With the right internal heat, the conditions on a rogue planet could support life forms that are very different from those on Earth, but still capable of thriving in their own unique environment. The discovery of life in a subsurface ocean on a rogue planet would not only expand our understanding of where life can exist, but it could also reveal new insights into the resilience and adaptability of life in extreme environments. Rogue planets, which drift through space without the light or heat of a nearby star, pose a unique challenge for astronomers. These planets are difficult to detect, making it hard to study their conditions or spot any signs of alien life. The absence of a star means that rogue planets don't emit light like other planets or stars, which makes them practically invisible to traditional telescopes. Without the usual signals we rely on, like starlight or the heat that a planet might reflect, rogue planets remain hidden in the vastness of space. This stealthy nature of rogue planets also complicates the search for extraterrestrial civilizations. On Earth, scientists have developed techniques to detect signals from other civilizations, such as radio waves or lasers. These methods rely on the assumption that the signals would travel through space and reach us, similar to how we send signals to space in search of alien life. However, detecting artificial signals from a rogue planet is much more difficult. A rogue planet might have a civilization living on it, but without the usual signs like the warmth of a star or light reflecting off the planet's surface, spotting such a civilization becomes a needle in a haystack situation. One of the biggest problems in detecting rogue planets is that they don't produce their own light. Unlike stars, which shine brightly, or moons, which reflect light from a nearby star, rogue planets are dark. This makes it very hard to locate them. Traditional methods of finding planets rely on their interaction with nearby stars. For example, astronomers can observe how a planet affects the light of a star, or they can spot the dimming of a star as a planet passes in front of it. This method works well for planets that orbit stars, but it's nearly impossible to apply to rogue planets because they don't have a nearby star to interact with. Astronomers have developed a technique called gravitational microlensing to spot rogue planets. This method involves observing how the gravity of a planet can bend and magnify the light from a distant star. When a rogue planet passes in front of a star, its gravity can briefly alter the star's light in a way that can be detected. While this technique has led to the discovery of some rogue planets, it's still not foolproof. For one, rogue planets are often distant, and the chance of a rogue planet passing in front of a star in such a way that it creates a detectable signal is low. This means that many rogue planets go unnoticed, and any potential civilizations living on them are even more difficult to find. If a rogue planet does harbor a civilization, the challenge grows even more complicated. A civilization on such a planet would not have the advantage of a nearby star to help send out signals. This means they would need to find other ways to communicate with the outside world, assuming they are trying to make contact at all. The lack of a star would also limit their ability to use traditional energy sources. A civilization living on a rogue planet would likely need to rely on internal energy sources, like geothermal heat, or possibly a form of energy that we are not yet aware of. Detecting artificial signals from such a planet would require advanced technology and methods far beyond what we currently use. The challenge of detecting signals from a rogue planet becomes even more complex when considering the vast distances between stars and planets in the galaxy. Even if a civilization on a rogue planet were trying to send signals, those signals would have to travel through empty space with no star to reflect or amplify them. These signals would likely be faint and would dissipate quickly as they traveled through the darkness of space. Unless the civilization was using a very powerful signal or some other advanced technology, their attempts to communicate would be nearly impossible to detect from Earth. Another aspect that makes rogue planets difficult to study is their isolation. Most planets that orbit stars are part of a solar system, meaning they are bound by gravity to a central star. This creates a predictable pattern for how the planet moves and behaves. Rogue planets, however, are not bound to any star and instead drift through space. This makes their orbits unpredictable, and it also means they could be located anywhere in the galaxy. Their movements are much harder to track, and without a predictable orbit, it's nearly impossible to know when or where to look for them. Given the lack of light and warmth, a civilization on a rogue planet would also face a very different set of challenges. Life on a rogue planet would need to adapt to the extreme cold of space. Without the warmth of a star, the planet would be frigid, and any life that exists would likely be deep below the surface, possibly in subsurface oceans, heated by the planet's internal energy. These oceans could provide a stable environment for microbial life, or even more complex organisms. But the surface of the planet would be inhospitable. Any civilization on a rogue planet would need to find ways to harness the planet's internal energy, like geothermal heat, to survive. This kind of civilization would be very different from those on planets with stars, where sunlight and solar energy provide an easier source of power. For example, imagine a civilization that lives deep beneath the surface of a rogue planet. They might rely on geothermal energy to power their technology, using heat from the planet's core to create energy, or to keep their environment warm enough for life to survive. They might even develop advanced methods of harnessing this energy, such as creating artificial suns or using other forms of energy that we have not yet discovered. This civilization could be just as advanced as ours, but without the ability to reflect light or communicate in the same way we do, they would remain undetected. The challenge of detecting alien civilizations on rogue planets might seem daunting, but it also opens up new possibilities. If these civilizations exist, they could be using technologies and methods that are completely different from anything we expect. They might be operating in ways that don't rely on sunlight or traditional forms of energy. They could be communicating using signals that we are not yet capable of detecting, or they could be using advanced forms of technology that don't emit detectable signals at all. In the end, the search for civilizations on rogue planets is a difficult task, but it is not impossible. As technology advances, we may develop new methods of detecting faint signals or identifying subtle signs of life that we cannot yet detect. However, the absence of a star makes these planets stealthy and elusive. Even if civilizations exist on rogue planets, they could remain hidden from us for a long time, making them one of the most challenging frontiers in the search for extraterrestrial life. Rogue planets are a fascinating category of celestial bodies, roaming through space without the warmth of a star. Because of this, they are often thought to be inhospitable, but there are factors that could allow life to thrive on these planets. One of these factors is the possibility of strong magnetic fields. If a rogue planet has a strong magnetic field, it could act as a protective shield against cosmic radiation, much like Earth's magnetic field does. This protection could create an environment where life forms, especially microorganisms, could survive despite the planet's extreme conditions. On Earth, the magnetic field plays an essential role in shielding life from harmful radiation. The Sunday constantly emits a stream of charged particles known as the solar wind. If this radiation were not deflected by the Earth's magnetic field, it would strip away the planet's atmosphere and expose the surface to dangerous levels of radiation. Without the magnetic field, life on Earth could not exist as we know it. A similar magnetic field on a rogue planet could provide the same kind of protection. Cosmic radiation comes from a variety of sources, including distant stars and even from the galaxy's center. These high-energy particles constantly bombard any planet that lacks the protection of a magnetic field. Without a shield, this radiation can damage molecules and cells, making it extremely difficult for life to survive, particularly for life forms that rely on complex molecular structures. Cosmic radiation is especially dangerous for organisms that live on the surface or near the atmosphere. It can cause mutations in DNA, interfere with the production of proteins, and degrade the atmosphere. This would make the surface of a rogue planet an almost impossible environment for life. However, if a rogue planet has a strong magnetic field, it could protect any potential life by deflecting much of this harmful radiation. A planet's magnetic field is generated by the motion of molten metals inside its core, much like Earth's dynamo effect. This magnetic field extends into space and forms a bubble around the planet called the magnetosphere. The magnetosphere acts as a shield, protecting the planet's surface from the harmful effects of cosmic radiation by deflecting charged particles away from the atmosphere. For example, consider a rogue planet that has a solid core capable of generating a magnetic field. Even though the planet might be far from a star and exposed to harsh cosmic radiation, the magnetic field could keep the radiation from reaching the surface. In this scenario, the planet might be cold and dark on the surface, but beneath that layer of protection, life could persist, similar to how life on Earth thrives under the protection of our magnetic field. The planet's atmosphere would remain intact, and the surface conditions could be more stable for life to exist, especially if there were liquid water beneath the surface. This protection is particularly important because without it, a rogue planet's atmosphere would be vulnerable to being stripped away. On Earth, the magnetic field protects our atmosphere, allowing gases like oxygen and nitrogen to remain intact, which are essential for life. If a rogue planet had no magnetic field, the same cosmic radiation could erode its atmosphere, slowly stripping it of the elements necessary to support life. The lack of a magnetic field could make it nearly impossible for any kind of life to develop or survive, even if the planet had a stable source of internal heat. If a rogue planet's magnetic field is strong enough, it could also influence the chemistry of the planet's atmosphere and surface, creating conditions that are more conducive to life. For instance, the magnetic field could help prevent the breakdown of important gases like water vapor, carbon dioxide, and methane. These gases play crucial roles in supporting life. Without a magnetic field to protect the planet from cosmic radiation, these gases might break down or escape into space. The presence of a magnetic field could help keep these gases stable, which might be important for maintaining liquid water, one of the most important ingredients for life. Think of a rogue planet with an internal heat source, like tidal heating or radioactive decay, that keeps a subsurface ocean liquid beneath a thick layer of ice. Without the magnetic field, the planet's atmosphere would be vulnerable to cosmic radiation, and the ocean beneath the surface might freeze over time. But if the rogue planet has a strong magnetic field, the atmosphere could be preserved, and the ocean could remain liquid. In this case, the protection offered by the magnetic field would act as a stabilizing force, allowing life to potentially exist in the liquid water under the surface. The idea of life on rogue planets with magnetic fields also opens up new possibilities for the search for extraterrestrial life. Traditionally, astronomers have looked for planets within the habitable zone of stars, where liquid water could exist on the surface due to the heat of a nearby star. But rogue planets, with their ability to generate internal heat and protect themselves with a magnetic field, offer a different approach. Even if these planets are far from a star, their magnetic fields could provide a stable environment for life to thrive, making them worth considering in the search for life beyond our solar system. Moreover, the magnetic field of a rogue planet could also create unique conditions for the development of life. On Earth, the magnetic field has played a role in the evolution of life by shielding the planet from harmful radiation, which allows life to thrive on the surface. A similar process on a rogue planet could protect potential life forms from radiation that might otherwise kill or damage cells. Over time, life could adapt and evolve in this protected environment, leading to the development of complex ecosystems. This idea is also supported by the fact that we already know that life can exist in extreme environments on Earth. In places like deep ocean vents or underground caves, life has evolved to survive without sunlight and under high levels of radiation. These organisms have developed specialized mechanisms to cope with harsh conditions, much like life on a rogue planet might. The magnetic field could offer the same protection that allows life to survive in extreme conditions on Earth, but in an environment where sunlight is completely absent. The combination of internal heat and a strong magnetic field could make rogue planets some of the most interesting objects in the search for extraterrestrial life. While these planets may seem inhospitable at first, the presence of a protective magnetic field could create conditions where life could survive, even without the warmth of a nearby star. This shield would help protect the planet's atmosphere and surface, allowing life forms to thrive in environments that might otherwise be uninhabitable. The magnetic field of a rogue planet could be a key factor in determining whether it can support life. If the field is strong enough to protect the planet from cosmic radiation, it could create an environment where life could develop and flourish. This possibility suggests that even in the cold, dark regions of space, life may have the chance to thrive, hidden away beneath the surface of rogue planets. The protection, offered by a strong magnetic field, could provide the stability needed for life to exist, despite the planet's starless nature. Rogue planets, which drift through space without the heat and light of a nearby star, are often seen as inhospitable. The idea of life on such a planet might seem far-fetched, given the extreme cold and lack of sunlight. However, there's a factor that could make these planets more welcoming than we might think: tidal heating. Tidal heating occurs when a planet experiences gravitational interactions with nearby objects, and these interactions can generate heat deep inside the planet. This heat can help maintain liquid water, which is essential for life, and create conditions that support life, even in the absence of a star. Tidal heating happens when a planet is pulled on by the gravity of another object. For example, if a planet has a moon or passes near a massive planet or star, the gravitational forces acting on the planet cause it to stretch and contract. This stretching creates friction inside the planet, and friction generates heat. The more the planet is stretched and compressed, the more heat is produced. This heat can accumulate over time, warming the planet's interior. If the planet has a subsurface ocean, this heat can keep the water liquid, even in the cold vacuum of space. One of the best examples of tidal heating is found on Jupiter's moon Europa. Europa is a frozen world, but beneath its icy surface, scientists believe there is a vast ocean of liquid water. The heat that keeps this ocean liquid comes from tidal heating. Europa orbits Jupiter in an elliptical orbit, which means that the gravitational pull from Jupiter varies as the moon moves through its orbit. This causes Europa's shape to stretch and flex, generating friction within the moon's interior and releasing heat. This heat prevents the water beneath the ice from freezing solid, creating a stable environment where life could potentially exist. Similarly, a rogue planet could experience tidal heating if it has a moon, or if it passes near another massive object. The forces involved could be strong enough to warm the planet's interior, keeping any subsurface oceans in a liquid state. The presence of a liquid ocean is crucial because it provides a stable environment for life. Without liquid water, life as we know it would be impossible. In this way, tidal heating could make a rogue planet more suitable for life than it would be based solely on its distance from a star. This process could work in a variety of ways. A rogue planet could have moons that exert tidal forces on the planet. If these moons are large enough and close enough, their gravitational pull could create significant heating in the planet's interior. The tidal forces would cause the planet to flex, generating heat from friction, which could prevent the water beneath the surface from freezing. This would create a stable environment for life to develop. In some cases, a rogue planet might pass near another massive object, like a gas giant or even another star. The gravitational interaction between the rogue planet and the nearby object could cause tidal heating. This could be especially important for rogue planets that are far from any star. Without a nearby star to provide warmth, these planets would be freezing cold on the surface. However, tidal heating could keep the interior of the planet warm enough for life to survive. The heat generated by tidal forces is not limited to just warming the planet's interior. It could also affect the planet's surface and atmosphere. For example, if a rogue planet had a thick atmosphere, the heat generated by tidal forces could help to maintain stable temperatures on the surface. The planet's atmosphere could trap heat and prevent it from escaping into space, much like the greenhouse effect on Earth. This would further stabilize the environment and create conditions that could support life. The combination of tidal heating and internal heat from the planet's core could provide a stable energy source for any life forms living on the rogue planet. In the absence of sunlight, these organisms would need to rely on other sources of energy, and tidal heating could be a key factor in making that possible. Life forms could use the heat and chemicals found in the subsurface ocean to survive. Similar to life found around Earth's deep-sea hydrothermal vents, life on a rogue planet might rely on geothermal energy rather than sunlight to fuel biological processes. Tidal heating could also have an impact on the geology of the planet. The constant stretching and contracting of the planet's surface could lead to volcanic activity, which would release heat and gases into the subsurface ocean. This could create a rich environment where life could thrive, much like the deep ocean ecosystems that depend on heat and chemicals from Earth's volcanic vents. These volcanic processes could also help to maintain the planet's atmosphere, preventing it from being stripped away by cosmic radiation or other harsh conditions in space. The presence of tidal heating could make a rogue planet much more dynamic than it would otherwise be. A planet without any external forces might be cold and dead, with no movement or energy to drive processes like volcanic activity or ocean circulation. But with tidal heating, the planet becomes more active. This movement and energy could help create a stable, habitable environment for life to evolve and survive. Imagine a rogue planet that has a large moon orbiting it. The gravitational pull from the moon causes tidal forces to stretch and compress the planet, generating heat deep inside. This heat prevents the water beneath the planet's icy crust from freezing, and the ocean remains liquid. Over time, life might evolve in this subsurface ocean, using the heat from the planet's interior and the minerals in the water to survive. This kind of life might be very different from life on Earth, but it would still be based on the same basic principles of chemistry and energy. Alternatively, a rogue planet might not have moons, but could pass near a gas giant or another star. The gravitational interaction between the two bodies could cause tidal heating, providing the necessary warmth to support life. In this case, the planet might not have a constant source of heat, but as long as the tidal forces are strong enough, the heat generated by the friction could be sufficient to keep subsurface oceans liquid and stable for long periods of time. Tidal heating could also play a role in determining the size and type of life that could evolve on a rogue planet. The amount of heat generated by the tidal forces would affect the temperature of the subsurface ocean and could influence the types of organisms that could survive there. For example, if the tidal heating is significant enough, the subsurface ocean could become a warm, rich environment, potentially supporting a wide variety of life forms. On the other hand, if the tidal heating is weaker, the ocean might remain colder, and life would need to adapt to more extreme conditions. In any case, tidal heating is a powerful force that could make rogue planets more hospitable than previously thought. By generating internal heat and keeping subsurface oceans liquid, tidal forces could create the right conditions for life to thrive, even without the presence of a star. The idea of advanced civilizations existing on planets far from stars might seem strange at first. After all, on Earth, life relies heavily on the energy provided by the sunday. But life on Earth has also adapted to survive in extreme environments where sunlight is not available. One of the most intriguing examples of this is life around deep-sea hydrothermal vents, where organisms thrive without sunlight, using heat from the Earth's core and chemicals from the ocean floor. If life can adapt to such extreme conditions on Earth, it's possible that alien civilizations could evolve similarly on planets without stars. Harnessing alternative energy sources such as geothermal or chemical energy. On Earth, deep-sea vents provide a rich environment for life forms that do not rely on sunlight. Instead, these organisms use chemical energy in the water, particularly sulfur compounds, to fuel their biological processes. These organisms are called extremophiles, and they thrive in conditions that would be inhospitable to most life forms. Some of these extremophiles even form the base of entire ecosystems, relying on the heat and chemicals from the vents rather than photosynthesis. This shows that life can not only survive, but also thrive in environments without sunlight. If life on Earth can adapt to such extreme conditions, why couldn't alien civilizations do the same? Rogue planets, which do not orbit a star, are often considered cold, dark places, far from the energy and light provided by a nearby sun. However, these planets can have other energy sources, such as geothermal energy, that could support life. A rogue planet could generate internal heat from processes like tidal heating or radioactive decay. Tidal heating happens when a planet experiences gravitational forces from nearby objects, like moons or other planets, which cause the planet to stretch and compress. This generates friction and heat, which can warm the planet's interior. If the planet has a subsurface ocean, this heat could keep the water liquid, creating a stable environment for life. Similarly, radioactive decay inside the planet's core can provide another source of heat. Just as Earth's core produces heat through the decay of radioactive elements, a rogue planet could maintain internal warmth for long periods. This geothermal energy could create the right conditions for life to survive, even though the planet is far from a star. If life can adapt to use these alternative energy sources, it is possible that advanced civilizations could develop on such planets, using the planet's internal heat or chemical processes to fuel their technology. If an advanced civilization were to evolve on a rogue planet, they might develop technology that harnesses geothermal energy in the same way we use it on Earth. On our planet, we already tap into geothermal energy for power, using the heat from the Earth's core to generate electricity. An alien civilization might use similar methods, perhaps developing advanced geothermal technology that allows them to harness the heat from their planet's interior. This technology could power everything from cities to spacecraft, relying on the planet's natural energy rather than energy from a star. Another possible source of energy for an advanced civilization on a rogue planet could be chemical energy. Life forms on Earth, particularly those living around deep-sea vents, use chemicals like hydrogen sulfide or methane to produce energy. These organisms don't need sunlight at all. They rely on the energy from the chemicals in their environment. If life evolved on a rogue planet, it might follow a similar pattern, using chemicals present in the planet's oceans or core for energy. Over time, the civilization might develop ways to extract and refine these chemicals, using them to power their society. The idea of a civilization using chemical energy is not purely theoretical. On Earth, some of the earliest life forms likely evolved to use chemicals from their environment, rather than sunlight. Over time, these life forms adapted and became more complex, eventually leading to the development of intelligent beings. On a rogue planet, life might follow a similar evolutionary path, adapting to use the planet's natural resources for energy. An advanced civilization on such a planet could have a technology based entirely on harnessing geothermal and chemical energy, allowing them to power their cities and conduct space exploration, all without needing the light of a star. In addition to geothermal and chemical energy, advanced civilizations on rogue planets might also develop technology that makes use of the planet's natural resources in other ways. For instance, they might use the planet's magnetic field to generate power, similar to how we use magnets in generators on Earth. A rogue planet with a strong magnetic field could provide a stable source of energy for a civilization that knows how to harness it. Over time, they could learn to manipulate the planet's magnetic field to create energy for everything from communication systems to propulsion for space travel. The key point is that an advanced civilization on a rogue planet would not need to rely on sunlight or stars to power their society. Instead, they would adapt to their environment and use the natural energy sources available to them. Just as life on Earth has adapted to survive in extreme environments, like deep-sea vents, alien life could evolve to harness geothermal and chemical energy, allowing them to create their own sources of power and develop advanced technologies. These civilizations might be very different from those on Earth, but they could be just as advanced, using alternative energy sources to fuel their growth and exploration. In terms of their potential for technological development, these civilizations would likely need to be resourceful and innovative. Without the light of a star, they would have to find ways to sustain their energy needs using the resources available on their planet. This might lead to the development of unique technologies that we have not yet imagined. For example, they might develop ways to convert the heat from the planet's interior into usable energy, or they might develop chemical processes that allow them to extract and use the natural chemicals found in the planet's ocean. As they develop, these civilizations might also face challenges that we don't typically encounter on Earth. For example, they would need to find ways to protect their technology from the harsh conditions of space, such as cosmic radiation. Without the shielding effect of a star's magnetic field, their planet might be more vulnerable to radiation, so they would need to find ways to protect their technology and their environment. However, the fact that life and civilizations can adapt to extreme conditions suggests that these challenges could be overcome with the right technology and resourcefulness. In the search for extraterrestrial life, astronomers have mostly focused on planets that orbit stars, particularly those in the habitable zone, where liquid water can exist on the surface. However, the possibility of advanced civilizations on rogue planets opens up a new area of exploration. These planets, far from stars, may be more than just cold, dark worlds. They could be home to life forms that have evolved to use alternative energy sources like geothermal and chemical energy. Just as life on Earth has adapted to survive in extreme environments, alien civilizations could adapt to their starless worlds, creating technology and societies that rely on the natural energy resources of their planet. In the end, rogue planets may offer a completely new perspective on the search for life. They may not need stars to support civilizations. Instead, life could evolve to use the energy sources provided by the planet itself, creating advanced societies that exist in the cold, dark reaches of space. Rogue planets are fascinating objects that move through space without a star to provide warmth or light. They are unlike other planets that orbit stars, and this makes them much harder to detect. Current telescopes and space observatories, which are designed to find planets that orbit stars, struggle to identify rogue planets. These planets don't emit their own light like stars, and they don't reflect sunlight like moons. As a result, rogue planets remain hidden in the vastness of space, making it difficult for astronomers to study them or look for signs of alien life. One of the main reasons that rogue planets are so hard to detect is that they do not shine or give off light. Traditional telescopes rely heavily on detecting light from distant objects. Planets that orbit stars reflect light from their parent star, making them visible to telescopes. For example, when a planet passes in front of a star, it causes the star's light to dim slightly. This phenomenon, known as a transit, allows astronomers to detect the presence of a planet. However, rogue planets do not have a star nearby, so they do not reflect light in the same way. Without light or any other clear signals, rogue planets remain nearly invisible to most telescopes. Another challenge in detecting rogue planets is their movement. Most planets that orbit stars are part of a solar system, and their orbits are predictable. This makes it easier for astronomers to track them and detect their presence. Rogue planets, on the other hand, move through space without being bound to a star. Their paths are unpredictable, which makes it even more difficult to know where to look for them. Without an orbit around a star to guide them, these planets can drift in any direction across the vast distances of space. To detect rogue planets, astronomers have had to rely on indirect methods. One of these methods is gravitational microlensing. This technique involves observing how the gravity of a planet can bend and distort the light from a distant star. When a rogue planet passes in front of a star, its gravity causes the star's light to briefly brighten and then dim. This change in brightness, though small, can be detected by sensitive telescopes. However, this method only works when the rogue planet happens to pass directly in front of a distant star. Since rogue planets are not tied to a predictable orbit, the chances of them passing in front of a star in such a way are relatively low. As a result, only a small number of rogue planets have been detected using gravitational microlensing. Another method that astronomers use to try to detect rogue planets is infrared imaging. Some rogue planets might still emit a faint amount of heat, even though they don't have a star. This heat could be detected using infrared telescopes, which are sensitive to the heat emitted by objects. However, the amount of heat that a rogue planet emits is much lower than that of a star, making it difficult to spot. Only planets that are large or young enough to still retain significant heat might be detectable in the infrared spectrum. Most rogue planets, especially older or smaller ones, would likely be too faint to detect using this method. Even with these methods, astronomers have only found a handful of rogue planets so far. The number of rogue planets in the galaxy is still uncertain, and many of them likely remain hidden from view. Some estimates suggest that there could be as many or even more rogue planets in our galaxy as there are stars. This means that the potential for discovering rogue planets is vast, but our ability to detect them is limited by current technology. Even though we may have the tools to find rogue planets, we are still in the early stages of exploring these objects. The challenge of detecting rogue planets becomes even more complicated when we consider the possibility of life on these planets. While astronomers have developed techniques to find planets that orbit stars, detecting signs of life on rogue planets is even more difficult. Life as we know it on Earth relies on a combination of factors, including warmth from the sunday, liquid water, and an atmosphere. Rogue planets without a star are much colder, and they are likely to have no surface water or atmosphere in the way that planets like Earth do. However, life could still potentially exist on rogue planets if they have internal heat sources, such as geothermal energy or tidal heating. For life to exist on a rogue planet, there would need to be some form of energy source that could support biological processes. Just as life on Earth thrives around deep-sea hydrothermal vents, life on a rogue planet could potentially survive in subsurface oceans heated by the planet's core or by tidal forces. This heat could create a stable environment where life could develop and evolve even without sunlight. But finding evidence of such life is incredibly challenging. Traditional methods of searching for life, like looking for signs of water or searching for biosignatures in the atmosphere, may not apply to rogue planets, as these planets likely have no atmosphere and no surface water to study. To detect life on rogue planets, astronomers would need to develop new techniques that are specifically tailored to these unique conditions. For instance, instead of looking for signs of water or an atmosphere, scientists might need to focus on the planet's internal heat and look for chemical signatures that could indicate biological activity. The challenge of detecting life on rogue planets is compounded by the fact that these planets are already difficult to find in the first place. Even if a rogue planet has life, it might not be possible to detect it with current technology. There are also other factors that make the search for rogue planets and alien life difficult. The vast distances between stars and planets in the galaxy make it hard to study these objects in detail. Even if we could detect a rogue planet, it would likely be located far from Earth, making it challenging to send probes or gather detailed data. Space missions that travel to distant planets take years or even decades, and a rogue planet's movement through space would make it even harder to catch up with. Despite these challenges, astronomers are optimistic that advancements in technology will improve our ability to detect rogue planets and study them for signs of life. New telescopes and space observatories, like the James Webb Space Telescope, may offer improved capabilities to observe distant objects, including rogue planets. These instruments may allow us to detect the faint heat emitted by rogue planets, or even spot subtle changes in the light of distant stars caused by gravitational microlensing. As our technology improves, our understanding of rogue planets and their potential for harboring life will continue to grow. For now, the detection of rogue planets remains a complex and difficult task. The absence of a star means that traditional methods of detection, like looking for reflected light or studying a planet's orbit, are not effective. Indirect methods, such as gravitational microlensing and infrared imaging, can help, but they are still limited in their ability to find and study these elusive objects. Even though rogue planets remain hidden for now, the search for them continues, and the potential for discovering alien life on these starless worlds remains an exciting frontier in astronomy. The search for extraterrestrial intelligence, SETI, has traditionally focused on planets that orbit stars, mainly looking for signs of civilizations that might be using radio signals or other electromagnetic emissions to communicate. This search is based on the assumption that intelligent life would develop technology similar to ours, using energy sources like stars to fuel their activities. However, this approach has limitations, especially when it comes to rogue planets that do not orbit a star. These planets, though difficult to detect, might harbor civilizations that are using local resources in ways that could be detectable by electromagnetic emissions, such as artificial radio signals or energy generation technologies. Rogue planets are an interesting class of worlds because they are not bound to any star. Instead, they drift through the dark expanse of space, and their surfaces are typically cold and isolated. Without the light or heat from a nearby star, these planets might seem inhospitable, yet they could still provide the right conditions for life to exist. In particular, if a rogue planet has a source of internal heat, such as tidal heating from a moon or geothermal energy from the planet's core, it could create a stable environment where life could thrive. If life exists on a rogue planet, it might have developed in very different ways than life on planets that orbit stars. For instance, the civilizations on these planets might not rely on solar energy, but instead on local energy sources like geothermal energy or chemical processes. These energy sources might be harnessed in ways that could produce detectable signals, much like how we use electromagnetic waves on Earth to transmit information. A civilization on a rogue planet might use similar methods to communicate, power technology, or conduct industrial processes. The electromagnetic emissions from such technologies could potentially be detected by SETI efforts. Even though rogue planets are far from stars, they still exist within the vastness of the galaxy, and any signal powerful enough to reach us could provide a clue to their existence. The challenge here is that traditional SETI methods are designed to detect signals coming from stars. The signals from a rogue planet might be weaker or different, but they could still be detectable if we expand the search methods. One way to detect technosignatures on rogue planets might involve looking for specific frequencies or patterns of electromagnetic emissions that are artificial in origin. These emissions could come from various sources, such as power generation systems that harness geothermal or tidal energy. For example, if a civilization were to use a large amount of energy for technological purposes, they might emit radio waves or other electromagnetic signals as a byproduct of their activities. These signals might resemble the types of emissions that we generate on Earth, such as radio transmissions, radar signals, or even energy leaks from large machines. A scenario that illustrates this could be a rogue planet with a population that has built a complex energy infrastructure based on geothermal energy. Just like Earth uses power plants to generate electricity, an alien civilization might use the heat from their planet's core to run large machines. These machines could generate electromagnetic emissions in the process. If these emissions are strong enough, they could escape the planet's atmosphere and travel through space, much like how radio signals leave Earth. Even if the planet is far from a star, the electromagnetic emissions could still be detectable by sensitive instruments designed to search for technosignatures. Rogue planets may also have other energy sources that could produce detectable emissions. For example, if a civilization uses chemical processes to create energy, such as through the combustion of gases or chemicals extracted from the planet's subsurface, this could lead to specific emissions that can be identified. This might include patterns of radio waves or even heat signatures that are consistent with the use of technology. The key would be to identify signals that are not naturally occurring but instead produced by intelligent activity. The search for technosignatures on rogue planets would require a shift in the way we currently look for extraterrestrial life. Instead of focusing only on planets within the habitable zone of stars, astronomers would need to consider the possibility that life and civilizations could exist on planets that are starless. These planets may still possess the conditions necessary for life to develop, including internal heat sources, subsurface oceans, or protective atmospheres. By searching for electromagnetic emissions from these planets, we could expand the scope of SETI to include rogue planets that might otherwise be overlooked. There are also practical challenges in detecting technosignatures from rogue planets. Because these planets don't reflect light from a star, they are much harder to spot. Traditional methods of planet detection, like looking for dimming of starlight as a planet transits in front of its star, won't work for rogue planets. Instead, astronomers would need to use methods like gravitational microlensing, where the gravity of a rogue planet bends and distorts the light of a distant star. This technique has been used to detect rogue planets in the past, but it requires specific conditions for success. Even so, once a rogue planet is detected, SETI researchers could begin looking for signs of artificial emissions, even if the planet itself is far from any star. The challenge of detecting technosignatures is further complicated by the possibility that rogue planets might have different kinds of technology than what we are familiar with. For example, a civilization on a rogue planet might not rely on radio waves or electromagnetic radiation in the same way that Earth-based civilizations do. Instead, they might use forms of communication or energy generation that are difficult for us to detect with current technology. This could mean that while we are searching for signals, we might be missing subtle or entirely different forms of emissions that could be a sign of intelligence. Another consideration is the distance between Earth and any rogue planets that might harbor life. Rogue planets are scattered throughout the galaxy, often far from any nearby star. This means that even if a technosignature is emitted, it could take thousands or even millions of years to reach us. The vast distances involved would make detecting such signals a long-term effort, and it would require powerful telescopes and sensitive instruments to pick up even faint emissions. Despite these challenges, expanding the search for technosignatures to include rogue planets could be a significant step forward in the search for extraterrestrial intelligence. The idea that intelligent life could develop on a starless planet may sound improbable, but it's not impossible. With the right technology, we could detect emissions from civilizations using local energy sources like geothermal power or chemical reactions. By adjusting our search strategies, we might uncover signs of life in places we have not yet considered, such as on rogue planets, which are some of the most elusive and least understood objects in our galaxy. As technology continues to improve, we may find that the search for technosignatures on these hidden planets could reveal new and exciting possibilities in our search for alien life. Finding rogue planets presents a significant challenge for astronomers. These planets, unlike those that orbit stars, don't shine with their own light or reflect sunlight. Without the glow of a nearby star, rogue planets are nearly invisible to conventional telescopes. Their low luminosity and lack of direct emissions make it hard to detect them, using the same methods that work for planets that orbit stars. This makes the task of spotting rogue planets one of the most difficult in modern astronomy. Conventional telescopes are built to detect light from distant objects. Planets that orbit stars are easier to spot because they reflect light from their parent star. When a planet passes in front of a star, the light from that star dims slightly. This dimming effect, called a transit, is one of the primary ways astronomers detect exoplanets. Additionally, the gravitational pull of a planet causes slight shifts in the star's position, which can also be measured to identify planets. These methods rely on the presence of light, either from the planet itself or the star it orbits. But a rogue planet which doesn't reflect sunlight and has no star to give off light doesn't fit this pattern. Rogue planets, instead, drift through the vast emptiness of space, far from the warmth and light of any star. Without any light or heat, they don't emit radiation in the way stars or planets orbiting stars do. This makes it difficult to locate them, especially since astronomers typically rely on visible light or infrared radiation to find objects in space. Because rogue planets lack these emissions, they stay hidden in the darkness of space, far away from our detection capabilities. While rogue planets don't produce their own light, they might still emit some weak infrared radiation. This could come from internal heat sources, such as tidal heating or radioactive decay in the planet's core. Some young rogue planets might still retain heat from their formation, and others could be warmed by the gravitational forces acting on them if they have moons or pass near other large objects. However, the amount of heat emitted by rogue planets is relatively faint compared to the bright emissions of stars. Detecting this faint infrared radiation requires very sensitive instruments and advanced telescopes, which are not always able to detect the low levels of heat from these dark starless planets. The detection of rogue planets is also complicated by the fact that they are often far from Earth. Even though some rogue planets might be in our galactic neighborhood, their distance from Earth makes them incredibly difficult to spot. The vast spaces between stars mean that the light or heat from a rogue planet will have to travel much longer distances to reach us, and by the time it does, it may be too weak to detect. As a result, even if a rogue planet is relatively nearby in cosmic terms, it could still be nearly impossible to find with current technology. Astronomers also face the difficulty of knowing where to look. Most of the exoplanets we have discovered are part of star systems, and their positions are more predictable based on their orbits. Rogue planets, on the other hand, are not bound to any star, and their paths through space are much harder to predict. This makes it a challenge to know where to aim telescopes to catch a glimpse of these elusive planets. Because rogue planets are not part of any solar system, they do not follow the regular patterns that astronomers have come to rely on when locating other exoplanets. One of the more successful methods of detecting rogue planets is gravitational microlensing. This technique takes advantage of the fact that a planet's gravity can bend and focus the light of a distant star. When a rogue planet passes in front of a star, its gravity causes a temporary brightening of the star's light. This effect, though small, can be measured by telescopes. By studying these brief moments of brightness, astronomers can infer the presence of a rogue planet. However, gravitational microlensing requires the rogue planet to pass in front of a star in just the right way. This is a rare event, and while it has helped astronomers spot a few rogue planets, it remains a difficult and uncertain method for finding them. Even with gravitational microlensing, astronomers often find rogue planets only by chance. The rare alignment of a rogue planet's path with a distant star's light means that many rogue planets will likely remain undetected. This is compounded by the fact that many rogue planets may be far away, and the lensing effect they create is only noticeable if they happen to pass in front of a bright star. The probability of observing such an event is low, meaning that the majority of rogue planets will not be discovered using this method. While infrared imaging can also help detect the faint heat emitted by rogue planets, this is not a perfect solution. The amount of heat a rogue planet emits depends on several factors, including its size, age, and internal energy sources. Many rogue planets, especially older ones, may have cooled enough that their emissions are too faint to detect. Even young rogue planets, which might retain more internal heat, can be difficult to spot because they are so far from Earth. As a result, even with advanced infrared telescopes, the task of finding rogue planets remains a challenging one. Another challenge is that rogue planets don't emit the same kind of signals that astronomers typically look for when searching for extraterrestrial life. When astronomers look for signs of alien civilizations, they often focus on electromagnetic signals, like radio waves, which are commonly used by us to communicate and transmit information. However, rogue planets are not likely to emit these kinds of signals on their own. Any alien civilizations on these planets might use local energy sources like geothermal or chemical energy, which would likely produce very different emissions, if any. Detecting these types of technosignatures would require new methods of searching and a deeper understanding of how alien civilizations might utilize resources on a starless world. Despite the difficulties in detecting rogue planets, astronomers continue to develop new techniques to find them. The development of more sensitive instruments, like the James Webb Space Telescope, could help detect the faint emissions from rogue planets that current telescopes cannot. As technology advances, astronomers will be able to detect even fainter signals, making the discovery of rogue planets more likely. However, the challenges of detection will remain significant, and finding these planets will still require patience and persistence. In the search for rogue planets, it is clear that we are just beginning to scratch the surface. While these planets are difficult to detect due to their lack of light and their unpredictable paths, new techniques and better technology may eventually help us find them. These rogue worlds are elusive, but they represent an exciting frontier in the study of exoplanets, one that promises new discoveries and insights into the nature of planets, life, and the universe itself. Rogue planets are a mysterious and intriguing type of world that drifts freely through space without the gravitational pull of a star. They wander the galaxy, unbound and unpredictable, and this movement could offer interesting possibilities for exploration or even contact with other civilizations. As these rogue planets pass through star systems, they present a fleeting opportunity for any observers or travelers to study or possibly interact with them. Though they might seem isolated and cold, rogue planets could harbor advanced life, providing the chance for unexpected encounters with alien civilizations. Imagine a rogue planet that passes near a star system with intelligent life. While the planet is not bound to a star, it could come close enough to another solar system to be noticed by observers. A rogue planet's passage through a star system could create a window of opportunity for exploration. If an advanced civilization exists on this wandering planet, the close encounter might give them the chance to detect signals or even make contact. The planet's passage could be short, lived, but in that moment, it could open a door for discovery and potential exchange of knowledge. Rogue planets are difficult to study because they do not emit their own light like stars, and they are not bound to a star's gravitational pull, making their paths unpredictable. However, their travels could bring them into the vicinity of star systems with advanced life forms. If a civilization on a rogue planet were capable of interstellar communication, they might send out signals into space, much like we do with radio waves and other electromagnetic transmissions. These signals could potentially be picked up by civilizations in the star systems the rogue planet passes through, providing a rare opportunity for contact. For instance, as a rogue planet passes near a solar system, it might send out a signal, and an alien civilization in that system could intercept it, opening the door for communication. On the flip side, the civilization on the rogue planet might be able to detect signals from the star systems they pass through. If they have developed advanced technology, they might have the capability to detect electromagnetic emissions from distant star systems. This would allow them to notice the presence of other civilizations in the path of their wanderings. While the chances of such a direct interaction are slim, the passing of rogue planets could still present a rare opportunity for civilizations to learn of each other's existence. If the passing rogue planet has a civilization capable of technological advancements, it might even develop the means to send out signals intentionally, similar to the search for extraterrestrial intelligence, SETI, that we conduct on Earth. Rogue planets, due to their unpredictable paths, could travel through many different star systems over long periods of time. While these opportunities for interaction may be fleeting, they are not impossible. If a rogue planet's orbit takes it through a star system at a time when a civilization on that planet is technologically advanced enough to detect signals or communicate, it could spark an interaction. These encounters would be brief, but in the right circumstances, they might lay the groundwork for future communication or exploration between civilizations. The idea that a rogue planet could serve as a temporary bridge between different civilizations is an exciting prospect for those interested in the search for alien life. The movement of rogue planets through star systems is not just a chance for potential communication. It also offers a unique chance for direct exploration. If a rogue planet passes through a star system, it might present an opportunity for researchers or space missions to send probes to study it. Even though the planet would be difficult to reach due to its constant movement, the close encounter could provide valuable data on its composition, atmosphere, and any possible life forms. If a rogue planet harbors subsurface oceans or an atmosphere capable of supporting life, the short window of time when the planet is near a star system could provide a rare opportunity to study it in more detail. This encounter might be brief, but for those willing to take the risk, it could be an important step in understanding the diversity of planets in our galaxy. In the case that a rogue planet does have life, whether microbial or more advanced, it would face unique challenges due to its starless existence. Without the heat and energy of a nearby star, a rogue planet would need to rely on alternative sources of energy, such as geothermal or tidal heating, to sustain life. This type of energy might support ecosystems similar to those found in the deep oceans of Earth, where life survives around hydrothermal vents, using heat and chemicals rather than sunlight. A civilization on a rogue planet might have developed technologies based on geothermal energy or chemical reactions, allowing them to create a self-sustaining environment. If such a civilization encountered another advanced society, they might have developed completely different forms of technology, adapted to their starless world. This could offer a fascinating opportunity for the exchange of knowledge and ideas, as both civilizations would be accustomed to harnessing energy in unique ways. The ability for civilizations on rogue planets to interact with others would depend on their technological capabilities. A civilization that harnesses geothermal energy or uses advanced methods to detect and communicate via electromagnetic waves might be able to communicate across vast distances. They could send signals into space and perhaps even catch the attention of other civilizations as they pass through star systems. Similarly, if a civilization on a rogue planet developed a form of propulsion technology that allows them to travel through space, they might choose to explore nearby star systems or even make contact with other civilizations. The chances of finding or interacting with a rogue planet that harbours advanced life are slim. But the potential for such encounters is nonetheless fascinating. Rogue planets are not bound to any one star, so their paths through space are unpredictable. However, when they pass through star systems, they offer a temporary, fleeting chance to detect signals, learn about their conditions, and perhaps even encounter intelligent life. These interactions, though rare, could reshape our understanding of how life can survive in the galaxy and how civilizations might arise under very different conditions. While the odds of these encounters are low, rogue planets do represent a new frontier in the search for extraterrestrial life. Their ability to pass through different star systems offers a unique opportunity for exploration, communication, and discovery. Whether through signals sent across space or the chance for direct exploration, the passage of rogue planets through star systems presents a fleeting but exciting possibility for finding life in unexpected places.